Well, hello again. Welcome to Math 315, Analysis and Topology, and this is the third recording for Chapter 7. In the previous section, we looked at Raleigh's theorem, which, as I said there, was a kind of stepping stone to the more important and quite useful mean value theorem that we're about to look at, or the average value theorem. Mean's just another name for average here. And before I go through all the gory details, it's best to have a look at this geometrically, and we'll do that, and then we'll state the theorem, and then we'll have a quick look at the proof, and then look at some applications of it. So geometrically, it's one of those results that's geometrically fairly obvious, and you might wonder why on earth you'd want to, what you can actually do with it, but it turns out to be quite a very useful theorem. Here are the ingredients. You start off with a function, which I'm just going to draw a little curve here. There's my function f, and it's defined on some interval between a and b. So this is f of a here, and that's f of b up here. So there's my function. And what you do is you join the two endpoints together to form what's called a chord. And the theorem basically says that you can take this chord and you can slide it, keeping always parallel to it, you can slide it up, and eventually this chord will become a tangent to the curve at some point. The chord will eventually become a tangent to the curve at some point. That's what essentially the theorem says. Now, if the chord's becoming a tangent, if these are parallel to each other, then they have the same gradient. So we can work out the gradient of the chord. That's just the gradient of this line segment here. So what do? You take the difference in the y values, f of b minus f of a, over difference in the x values, the rise over the run, and that gives you the gradient of the chord. And this chord is going to eventually become a tangent to the curve, to the function f, somewhere. That is, there's some number psi. Again, if you don't like using psi, just put a c there. There's some point psi here where the gradient of the curve, which is just the derivative, is this gradient is equal to the gradient of the secant. That is, these two lines are parallel. So that's the geometry of it. Now let me state it a bit more formally. So here are the ingredients of it. And all these theorems conditions apply, as in the adds. So we have f is defined and continuous on some interval ab, so there's a function, it's nice and continuous, and it's differentiable on the open interval ab. You can get the derivative at all points along here. Then the theorem says that there is a point psi, put c if you prefer, there is a point psi somewhere in here, so that the gradient of the tangent to the curve, that's f dash to psi, is equal to the gradient of this secant. That is, it's f of b minus f of a on b minus a. And that's going to be our key formula we're going to be using. So that's our key formula. Now I'll just give a quick little proof of this. It follows by a little trick using Raleigh's theorem. We take this new function g of x, we take the old function minus a plus f of b minus f of a on b minus a times x minus a. So this bit in here is just really the line segment here, and you're subtracting that from this function f. And you'll see why we do this, because it turns out then that this new function g satisfies the conditions of Raleigh's theorem. That is, we're going to show that g of a and g of b are the same, and that will tell me then that this function has zero gradient somewhere in between, because that's what Raleigh's theorem says. So if I put x as a in, then look what happens. You get a minus a here is 0, so that all that term vanishes, and I just get f of a minus f of a, and that's all 0, and that's just 0. So g of a is 0. And if I put in b, well, what happens then? If I put b minus a in here, that b minus a cancels with that b minus a, and I'm just left with f of b minus, brackets, f of a, plus f of b minus f of a, because this bit cancels, And if you simplify all this, everything cancels out and you just get 0. So the function g is continuous because f is, and this is continuous. And it's differentiable because these functions are differentiable. It's got the same value at a as it has at b. And so by Rolle's theorem, there's a psi somewhere in here where the derivative is of g is 0. Now what's the derivative of g? Well, derivative of g is 0. I have to differentiate this expression in here. And what that's going to give me, of course, is this is a constant. That's going to differentiate to 0. So I'm going to get, when I differentiate through here, I'm going to get f dashed evaluated at psi minus, that goes to 0. Now these are all constants, so the derivative of this bit in here is just this number here multiplying the x. That's going to be the derivative. So I'm just going to get 0 equals f dashed of psi minus this expression here, and when I put it on the other side and simplify, I simply get this, which is our formula. So that's a little proof of the mean value theorem. Now the next little example is just to demonstrate the mean value theorem for this function. It's a quadratic, 6 minus 2x plus x squared on the interval minus 2 to 2. So here's a little demonstration of this here. So here's our function on the interval minus 2 to 2. So I'm just going to use that formula, f of b minus f of a over b minus a. So that's f of 2 minus f of minus 2 divided by 2 minus minus 2. Now I can simplify all that. So when I plug in 2 into here, I get 2 plus 6 minus 4 plus 4. And then I put minus 2 in here, I get this. Simplify all this, out pops minus 2. So here's the picture. There's the function. I've drawn it down here. There's the function defined on the interval minus 2 to 2. And there's the chord. And we've just shown that the gradient of this chord is minus 2. Now, the theorem says that somewhere in here, the gradient of this function also equals minus 2. So I differentiate the function. I get minus 2 plus 2x, and I want to know, where does this equal minus 2? Well, it clearly equals minus 2 and x is 0. So indeed f dashed of 0, then, that's the gradient of the tangent at 0, matches up with the gradient of the chord. So that's just a little illustration of the theorem. Well, as I mentioned, it may appear at first glance as a rather strange theorem, but you can do, in fact, quite a range of problems with it. We're only going to just do a small number of examples of this. It can be used to do all sorts of things, but I'm just going to limit what we do with it here. So we're going to apply, and I'll always use this wording when we do questions like this. I will always use this particular wording, so it's clear. We're going to apply the mean value theorem to the function f of t equals sine t on the interval from 0 up to some point x, where x is positive. Now the reason I'm changing from x's to t's here is because I want to use x as the end point of my interval. We're generally going to use x as the end point of our interval, so I can't use x in both places because it doesn't make sense. And we're going to use that to prove that sine of x is less or equal to x for all x bigger than 0, which is a nice result. So we know that sine is less than 1, but we can also show that sine of x is less than x. So for example, sine of a half is less or equal to a half, and so on. So here's the worked solution to this one, and this is how we're going to use the mean value theorem. So here's the function. F of t is sine t on the interval 0 x, where x is positive. Again, I'm using t's here, and I'll do that all the time because I want to use x as the end point of my interval. Now, the mean value theorem says this is my a, this is my b, so I've just written it down here again. It's f of b minus f of a on b minus a is f dashed of c where c is some number in the interval 0 to x. Now, by the way, we don't ever know what c is. The theorem never tells us exactly what the value of c is. It just says there is one. It tells us where it is. It's in this interval, but it doesn't tell us what it is. It just says there is a c and it lives somewhere between 0 and x, but we never know what it is. And in practice, I get rid of the c as quickly as I can when I'm applying this. Okay, so we plug everything in. So I take sine of x minus sine of 0 divided by x minus 0. That's my f of b minus f of a on b minus a. I differentiate sine, becomes cos, and I'm going to plug in, so it becomes cos t, and I'm putting t equal to c in. So I end up with this expression here at the moment. Now, we can simplify this. The sine of 0 is 0, so this just becomes sine x on x. Now again, we don't know what this c is, but the cos of whatever it is, its cosine can't be any bigger than 1. So when you see trig functions, you want to bound them, you just replace it with a 1 and use the inequality sign. So this is always less than 1. So I can now have, therefore, that sine of x on x is less or equal to 1. Now my x is positive, so I can multiply the x up to here without doing any damage to the inequality sign, and I get sine of x is less or equal to x. Second example here, and again I've worded it exactly the same way. It says you apply the mean value theorem to the function f of t is tan t on the interval 0 x. This time I'm going to let x be between 0 and pi on 4. And we're going to use that to prove that tan of x is bigger or equal to x for x in this interval. I've had to be a bit careful here because tan blows up at pi on 2, and so I didn't want to worry about infinite discontinuities and things. So I've just stopped x at pi on 4, but in fact this turns out to be true for all x, but I'm just, in this example, to avoid difficulties, I'm going to just make x between 0 and pi on 4. So here is the solution of this. So f of t is tan t, and on the interval 0x between in there. I should just comment here that f is continuous on the interval 0x, as long as x is between 0 and pi and 2, and f is differentiable. You have to check the conditions. It's differentiable on the open interval 0x. So I just check the conditions are correct, and then by the mean value theorem, again we just plug it all in. So we get f of x minus f of 0 over x minus 0. So f of that minus f of this divided by x minus 0. And that's going to equal the derivative of this function, that's with respect to t there. I differentiate this function with respect to t, and I'm going to put t equals c in. So I differentiate tan, becomes sec squared, and I replace the t with c, so I get sec squared c. Now here, f of x is tan of x, tan of 0 is 0, so again I just get tan x on x, and the derivative of tan is sec squared, and sec, of course, is 1 over cos, so sec squared is 1 over cos squared. Now as before, cos squared is less than 1. It's between 1 and minus 1, but when you square it, it's going to be less than 1. So I can turn both sides upside down. Everything now is positive. Take the reciprocal of both sides, then it's going to change the inequality sign. So 1 on cos squared is bigger or equal to 1. So that enables me to get rid of this term. Again, we don't know what this c is, but we know where it is, and the sec squared of c will always be bigger or equal to 1. And then again, because x is positive, I can multiply the x up the other side, and I get tan x is bigger or equal to x. And so that's the solution to that problem. One other example we're going to do, in fact you'll have one of these I think in the, I think one of something like this in the assignment 2. So again I use the same wording. When apply the mean value theorem to the function f of t is inverse tan of t. This time the interval is going to be the interval yx, where y is less or equal to x are any real numbers. So we're going to apply it to that, and we're going to use that to prove that inverse tan of x is uniformly continuous on the real line. Uniformly continuous on the real line. Yet another nice application of the mean value theorem. So here's the working for this example. So here's my f of t is inverse tan t, and I'm on the interval yx, where y is less or equal to x. So these are any numbers at all, as long as I take y to be less than x, so that the interval makes sense. Well, again, I'm going to apply the mean value theorem. So you take f of this one minus f of this one, f of x minus f of y, divided by x minus y, and that's going to be the derivative of this thing evaluated at c. Again, we don't know what c is, but we know where it is. It's somewhere in this interval between y and x. So into picture form, there's my y, there's my x, and then somewhere in here is my c. And of course we don't know what c is, we only know where it is. So plugging this in, I get inverse tan x minus inverse tan y over x minus y. Now when I differentiate inverse tan of t, you get 1 over 1 plus t squared, and of course we then have to replace the t with a c. So the derivative of inverse tan, you make sure you know all your derivatives of your inverse trig functions, so you get 1 on 1 plus t squared, and that's 1 on 1 plus c squared. Now the aim of the game is to get rid of this c as quickly as possible. So you say, well, what can I say about this? Well, it's 1 over 1 plus something. So think of c as a half or something. It's going to give you 1 over a number that's bigger than 1, and that's going to be less than 1. So that's less or equal to 1. So I can take the absolute value of both sides. Everything's positive because y is less than x, and this is positive, positive. So you can take the absolute value of both sides and then pull this up to the other side, and I get this formula here. Inverse tan of x minus inverse tan y is less or equal to absolute value x minus y. That's the first part. Now we're going to use this to show that f is uniformly continuous on the real numbers. So here's our usual mantra. We say given epsilon bigger than naught, put delta equal to, well, you can see what I've chosen there, but pretend for the moment I haven't got that there. So given epsilon bigger than naught, we're going to put delta equal to something. Then if x and y are within delta of each other, this is our definition for uniformly continuous, then we look at f of x minus f of y. So that's inverse tan x minus inverse tan y. And now using our lovely mean value result up here, this is less or equal to x minus y. But of course that's just less than delta, and I wanted it less than epsilon, so I just whack delta equal to epsilon, and this delta now depends only on epsilon, nothing else. And therefore inverse tan x is uniformly continuous. Now you'll see a similar question to this one in the assignment 2, I think. Well, one final thing to do before we for this section, I'm going to just again use the mean value theorem to prove this result, which is one that you would have known from school. You've just believed it, but probably never seen it proven. It says that if f is differentiable on the real line, if the derivative of the function is 0, then the function has to be a constant. You've used it the other way around at school. You've said, well, if I've got a constant, if you differentiate a constant, you get 0. This is the other way around. This says if the derivative is 0, then the function is a constant. You've tacitly used this when you do integration, because you pick up a plus c when you integrate. So if the derivative is 0, then the function is a constant. And this falls out quite neatly, in fact, simply using the mean value theorem. So here's a little proof of this. So here's our assumption. F is differentiable on R, and its derivative is 0 for all x. For any x you like, the derivative is 0. We're going to show that this f has to be a constant. Being a constant means it takes the same value. Whenever you put any number in place of x in your function, you get the same answer. That's what we mean by a constant. So again, I'm going to apply the mean value theorem to this f of t on the interval ab, where a and b are any numbers you like, but to make sense of this, I just need a less than b. So we take any numbers we like, a and b, a less than b, and I'm going to apply the mean value theorem. So we have f of b minus f of a over b minus a, as usual, equals the derivative at some point c inside this interval ab. Now, our assumption was that the derivative was 0 for all x, so in particular it's 0 at c. So this is equal to 0. I can multiply then both sides by b minus a, and that gives me f of b minus f of a is 0. That is, f of b equals f of a. That means these a and b are arbitrary. They're any numbers you like. So this says you can put any number you like in place of x in this function f, and you'll always get the same answer. In other words, f is a constant. And that is the last part of this recording. In the next one, we'll talk a little bit more about uniform continuity, and we're going to look at L'Hopital's rule.